So hi everyone, my name is Qian Xie. I'm a Cornell or PhD student. And as you have seen in the title, my work to introduce today is also related to Pandora's box. And basically I will introduce how we solve a machine learning problem called Bayesian optimization by using insights from Pandora's box. So what is Bayesian optimization? The motivation comes from many real-world applications, for example, hyperparameter tuning for transportation markets and A/B testing, where you want to find the best hyperparameter by running some experiments. However, while running these experiments, the cost may be expensive. And our goal is to optimize this expensive to evaluate black box function. How we mathematically model this goal in the Bayesian optimization framework, we assume the black box function is an unknown random function drawn from a Gaussian process prior. If you have not heard of Gaussian process, you can think of it as an infinite dimensional generalization of multivariate normal distributions. The mean and the variance of these Gaussian distributions represent the prediction and the confidence of your prediction. So you can view it as a decision-making under uncertainty problem. More formally, we want to find the global optimum by evaluating a set of points. However, since this function is expensive to evaluate, it's not practical to find the global optimum, particularly when your search domain is continuous and high dimensional. So we can adaptively evaluate a set of points, like say here, and then we update our posterior belief and get more and more information within a time budget T. Now our objective is to optimize the best observed value at time T. So why is this problem hard? First, you have a continuous search domain, which means that you have infinitely many choices, infinitely many points to evaluate next. And second, the function values are correlated. Those closer points have a higher correlation, and the further points are less correlated. And third, we have a hard budget constraint. As in continuous optimization, it's always not that clean to solve a constraint problem as solving an unconstrained problem. Moreover, traditional Bayesian optimization did not take explicit evaluation costs into account. What if you have heterogeneous evaluation costs? Even though there are some related works, but they haven't addressed it very well. So the optimal policy of Bayesian optimization is unknown, but can we convert it to a solvable problem? And the answer is yes. We can discretize the continuous search domain, for example, to grid points. We can also drop the correlation assumption and treat them as independent grids. So finally, we can, instead of having a budget constraint, we can incorporate the costs into the objective. And this is Pandora's box problem, which you have just heard. So maybe I can I can go over this part more quickly. Oh, here's the typo. It's not adaptively evaluate set of points. It's you adaptively open a number of random boxes. And you will see now the objective is to maximize net utility. But you can still find some similar structure in Pandora's box problem. It's just have a few difference. For example, here instead of maximizing the best observed value, we maximize the net utility. And instead of a continuous search domain, we have a discrete search domain. And instead of a fixed time budget T, now we can have a random stopping time T. Oh, also, we can particularly focus on Pandora's box with Gaussian distributions to match with our Bayesian optimization framework. So, what's the policy you can think of like solving this Pandora's box problem? Before diving into that Weizmann's Gittins policy, let me first introduce why a naive greedy policy can fail. So basically, the high-level idea of this naive greedy policy is that, okay, the simplest setting is that you have an open box with a value, say y best, and then you have a closed box. Then now you consider the expected improvement over the current best value adjusted by the costs. And thank you. And each time you can evaluate the box with the highest adjusted expected improvement. Okay, let's take a look at this example. So you have a deterministic Pandora's box with a high cost and some other cheaper boxes. Which one you would open first? So this naive greedy policy would open this expensive box first because the adjusted expected improvement is 2, while the adjusted expected improvement of other boxes is 1 in this example. So it will open this box first. And you will have an expected utility of 2 in this example. However, the optimal policy would open those cheaper boxes until finding reward 200. In expectation, you need 100 boxes, which will give you an expected utility of 100, which is much larger. And this policy is exactly the Gittins policy. And the high-level idea is that instead of computing expected improvement over the open box, you consider what's the equivalent value such that it's worse that you pay this cost to gain that expected improvement. And you compare the now you have an equivalent Gittins index to represent this closed box, and you can compare it with the open box. So the Gittins index of these cheaper boxes is 100, while the Gittins index of the closed box is 2. So now Gittins policy will open these cheaper boxes first, and it is the optimal policy. So now you have seen we have an optimal policy for this Pandora's box problem. You may wonder, is Gittins index policy good for Bayesian optimization? But before going to that, the first question to answer is how to translate it. So I will start from addressing the connection between the budget constraint and cost per sample first. So what is the optimal policy for a budget constrained Pandora's box? The answer is that there exists a budget dependent scaling factor such that if we solve Pandora's box with scale costs, we have a Gittins policy, and that Gittins policy is also optimal for this budget constrained Pandora's box. There's a prior work which solves for reward distributions with finite support, and we extend their results to general support, because you have seen, like in our setting, we need Gaussian rewards. But it can also apply to like other types of rewards. So next, I will briefly introduce the proof sketch of this result. So first, we can use Lagrangian relaxation to convert a constraint problem to an unconstrained problem. So now you have a Lagrange multiplier. And then we can use Lagrange multiplier theorem to switch the superior and the infimum. So if we call this thing as A lambda, we want to show the non-zero infimum of this thing exists. So the prior work shows that there are two possible cases. Okay, so this A lambda is a superior over a set of linear functions, so which is convex, but it can possibly be non-differentiable. Since the prior work assumes finite support, so there are finite breakpoints here, then we can simply apply envelope theorem to obtain the existence of the infimum. But what if we have infinite breakpoints? Thank you. Then we need a sharper envelope theorem, so which is included in our work. All right, so now you have seen that we can add a budget-dependent scaling factor to scale the costs to obtain the analytical form of this Gittins policy. And next, I will introduce how we incorporate continuity and correlation. Basically, how to incorporate Gaussian distribution, Gaussian process. The modification here is that we can, instead of using because in the independent world, you can just plug in the distribution and it's always the same. However, here now we can plug in the posterior distribution based on our observed data. And actually, this expected improvement part is a popular one-step heuristic called EI policy for uniform cost Bayesian optimization. And the ratio between this expected improvement and the cost is EIPC policy for cost-aware Bayesian optimization. And both policies can be arbitrarily worse. And we wonder whether our Gittins policy can have a much better performance. And the answer is yes. So we have run some experiments, and the results have shown that our PBGI policy can outperform baselines in both synthetic and empirical experiments. And the future work is that whether we can show a regret bound for our policy in theory. So for more experiment results, you can check our preprint on arXiv. Okay, to conclude, we propose an easy to compute policy for cost-aware Bayesian optimization, and it is effective. More importantly, we believe this framework can be beneficial to more complex Bayesian optimization problems by using some existing Gittins results. So for example, there is an extension to Pandora's box. Instead of like you just open the box to get the value directly, you can take multi-step to get the value. So that's like what we call the Go problem or Markovian multi-arm bandits. So we believe by borrow insights from those kind of work, maybe we can solve some free-solve Bayesian optimization where you can observe some partial feedbacks and you can also pause this process and to continue with other processes, which is very similar to these problems. And that's all. Thank you. Any questions?